Good afternoon. My name is Akash Solomon, and I will be presenting a presentation on the performance analysis of orthogonal frequency division multiplexing for reliable grayscale image transmission. This is in accordance for the course project for EEL 6509 wireless communication. So to begin with the topic, we rely on the use of communication systems in different spheres of our lives. So the most common implementation of these communication systems is to utilize the use of a single carrier communication system, which employs the use of symbols which would represent bits of binary information. By utilizing the use of symbols, we can represent this information in terms of quantifiable symbols to be used to be transmitted from the sender to the receiver. And this information should be sent without distortion to ensure that the receiver has received the message successfully and clearly. And in order to do that, we must ensure that the minimum symbol period should be greater than the delay between greater than the transmission delay, to ensure that the information is timely and appropriately synchronized and sent correctly. However, because of this minimum requirement where the symbol period must be greater than the transmission delay, it places a certain upper bound on the data transmission rate, which is inversely proportional to the symbol period. In accordance with this, because of the upper bound, there is one way to address the shortcoming, which would be to ensure the use of multiple carriers as opposed to a single carrier, so as to ensure that we are utilizing the maximum available resources to derive the maximum possible performance. Multi-carrier systems often make use of frequency division multiplexing, where the spectrum allotted is split into a number of different carriers, such that each of the channels are capable of carrying their own pieces of information or their own symbols in parallel, such as to maximize parallelism and maximize performance. However, as you can imagine, when multiple carriers have to share the same spectrum or the same bandwidth, there is a danger of interference arising from the channels being too close to each other, which causes a problem when it comes to the channels being so close to each other that the symbols themselves experience interference, or the channels themselves experience interference. So this interference manifests itself in the form of inter-channel interference, ICI, wherein the channels are not spaced appropriately, or that there is an interference in the symbol between symbols during communication, causing ISI. So in order to overcome these two obstacles, we make use of orthogonal frequency division multiplexing, which provides us as an attractive form of multi-carrier communication, where we will be able to utilize high data rates while also being able to avoid or diminish ISI and ICI. So, as I mentioned before, the advantages of OFDM involve that we will have a multi-carrier system where the carriers are close to each other and they share the same spectrum and the same bandwidth, without the risk or a diminished risk of ICI and ISI, while ensuring that we would have a number of low data rate channels to ensure that the symbol period would be long enough that it would be longer than the transmission delay for each of the channels, and thus would avoid the symbol interference or avoid ISI. So we will further explore how OFDM could be used in a communication system. So the data being expressed for an OFDM system could be represented in terms of a collection of bits, where a symbol is defined as a collection of information, and this collection of information could be used in different modulation schemes such as QAM, PAFK, and these symbols are used in the time domain by utilizing inverse Fourier transforms to ensure that the representation in the frequency domain is converted to its time domain, which would allow for the information to be parallelized as opposed to serial communication, so as to ensure that by converting it from a serial representation to a parallel representation, we would be able to achieve maximum throughput and maximum performance, while also guard against ISI and ICI. And one of the safeguards that we utilize is the use of a cyclic prefix, which is used in the form of a short segment of the frame or the short frame or the short message which we are transmitting, which is repeated and placed at the head of the signal so as to ensure that if there was a delay in the synchronization, that the signal would not suffer from the delay in the symbol being received. And so by using the cyclic prefix, we can ensure that the signal is still synchronized appropriately even though we don't receive it on time. So as I mentioned, the attractive feature of the OFDM system is that we utilize the use of orthogonality, where several carriers all lie in the same bandwidth of the same spectrum. And this is useful because we have to ensure that two signals are orthogonal, or that the integral of the product of the two signals must be zero over a certain time period as defined by this mathematical equation. This is possible when the two signals are sharing a multiple or an integer multiple of a common frequency. When this is caused, we can be sure that we will arrive at the correct output. So the objective of this project is to achieve a MATLAB implementation of the overall system model with a given channel description so as to achieve a idea of the parameters which are required and analyzed to be tabulated and depicted, which will provide the most optimal performance and image quality transmission for optimal bit rates and communication across different media. So here we have the overall communication system for an OFDM transmission, where we have our specific grayscale image acting as the source, which is split up into a number of frames. And these frames are divided in the frames divider and then parallelized in the serial to parallel converter, and then modulated into the frequency domain, and then allotted in terms of bins or different carriers in the IFFT bins allocation, and then finally being using the IFFT of the inverse fast Fourier transform to convert it to the time domain so that we occupy each of the different carriers in the time domain. And as we have discussed earlier, by utilizing the cyclic prefix to help fix delayed signals or to help synchronization, we use the cyclic prefix and convert it back to a serial signal and cascade these frames and send it over a communication channel. The communication channel that we utilize is modeled after AWGN, or additive white Gaussian noise, such as to simulate the characteristics of a typical communication channel, where it is then received at the receiver end, and the reverse of all of the operations which are occurring at the OFDM transmitter are achieved at the OFDM receiver. So we have the detection of the frames, serial to parallel, we remove the prefix, we convert it back to the frequency domain, demodulate the information, retrieve the original information, and convert it from a parallel to serial combination, cascade the frames, and retrieve our original information or our original image. So now that we know how the overall system implementation occurs in terms of modules, we have to use two particular characteristics so that we would know how to measure the overall system verification and the overall system performance. So we utilize two parameters, which is the bit error rate and the error pixel percentage, where we compare the number of the pixels which are incorrect from the original image and the new image, so that we can establish a measure of quality. And the bit error rate tells us the number of errors which are retrieved in the new image, so as to achieve the number of errors which are occurring in the new image, so we can establish a sign of quality as well. So for this purpose, we can use multiple modulation schemes such as DPSK, QPSK, 16-point PSK, or 256 PSK, and we make use of the variation in signal to noise ratio values or the channel characteristics to define what is the ideal size for the channel, what are the ideal values for this maximum system performance and for reliable transmission for a given grayscale image. So we consider the parameters that we utilize in the overall algorithm make use of IFFT of size 1024 with 400 carriers in the channel, and a clipping of 3 dB for the peak value of the power in the communication channel, such as to provide a clipping value for the amplitude of the channel. So once we compared the performance of the bit error rate and the received pixel percentage error with the SNR values for a given modulation scheme, we can see that the bit error rate is inversely proportional to the signal to noise ratio, and this is due to the fact that for higher complexity and for higher complex systems and higher modulation schemes, we would require extremely high sizes for the symbols, which would cause a minimum phase difference between the different symbols. And because of the minimum phase difference between different symbols, there's a high probability of bit error rates increasing, which is why, as illustrated, for the higher modulation schemes in 256 PSK, the bit error rate is very high and would require a correspondingly very high value of SNR to ensure that we have optimal performance. The negative performance and bit error rate is also reflected similarly in the received image pixel percentage error. So here we have the performance for the transmission of Lena, the famous image processing subject, where the left-hand side we have the actual image itself, the original image being transmitted, and these are the images which are retrieved for SNR for an SNR value of 0, for an SNR value of 5 dB, and for an SNR value of 10 dB. So what we notice is that for lower values of SNR, we can see that there's a greater level of distortion and a greater level of bit error rates and a larger value of percentage error in the pixel values, which causes a distorted image. But for higher values of SNR, the performance improves dramatically. Similarly, we see that for a higher value or a higher modulation scheme, we see that for the same values of the SNR as we saw with DPSK, we see that the performance has deteriorated even further, and this is because, as I mentioned earlier, higher complex modulation schemes would result in larger symbols and lower phase difference, causing higher bit error rates. The trade-off is that while there may be higher bit error rates as opposed to DPSK, we achieve the QPSK modulation with a much higher data transmission rate to retrieve the image. So while we can see that the images may be distorted ever so slightly, we notice that the overall image quality is still fairly good and it is not very negative. And this is because since we're making use of grayscale images, even if there are if there are errors in the image due to misinformation or wrong bits, misinformation in bits would relate to a few gray levels being misrepresented, and the human eye is not capable of perceiving large differences in gray levels. Although there may be errors in the bits, we don't perceive it in terms of gray levels. So this introduces an interesting trade-off where we can see that for a higher modulation scheme, even though we have a higher bit error rate, we can achieve an image in a much faster period of time. This is an abbreviation or an expansion of what I just explained with the trade-offs between the bit error rates for QPSK and DPSK and for higher modulation schemes. So in summary, we have achieved the overall system implementation in MATLAB using the OFDM model, and we have shown the attractive options due to the fact that there are multiple carriers while being able to use the same channel for all of the independent carriers. And I will now present the operation of the actual algorithm itself. So we have the overall algorithm here, which would be OFDM sim, which I will now run. And it will inquire for the file, which would be Lena in the file directory. We use the standard the standard parameters which I've indicated in the presentation. We make use of DPSK, for example. We use the same clipping as in the presentation with 3 dB, and we show that the signal to noise ratio in dB, we'll assume that it is 5 dB. Now we'll see the algorithm will be at work. and the OFDM signal has been transmitted, and now the OFDM model is being received, and we have the final image which has been received as Lena_OFDM, which if we were to take a look at,